an invited talk about AGN variability studies with Nancy Grace Roman Space Telescope from Triana, Almeyda. And you can take it away.
Great, so hopefully you guys can see my slides. As Jesse mentioned, I'm Triana Almeyda, and I'll be talking about AGN variability studies with the Nancy Grace Roman Space Telescope. If my slides will progress. Okay, so over the last few decades, much research has established that supermassive black holes are present in the centers of most, if not all, galaxies. These supermassive black holes grow by accreting infalling interstellar gas that's been disturbed, and this material forms the accretion disk. This disk is not only the source of fuel for the supermassive black hole, but also the engine that powers the AGN, converting the gravitational potential energy of the infalling matter into huge amounts of electromagnetic radiation, gas outflows, and jets of ionized plasma. So feedback from radiative and mechanical energy during the supermassive black hole growth phase has a major impact on the evolution of its host galaxy. So extensive studies have led to the development of this AGN unification model, which we see on the right, which attempts to explain the wide variety of observed properties that we see. There are four major components: the supermassive black hole, the accretion disk, the dusty torus, and the emission line regions. So as mentioned in the previous talk, AGN are typically divided into unobscured type 1 or obscured type 2 AGN, depending on whether they're oriented face on with respect to the observer's point of view or edge on. So light from the edge on type 2 AGN is obscured from the infrared to X-rays by this torus donut-shaped structure of the dusty molecular gas. So some basic observed properties of AGN are that they have a broad range of luminosities, they have strong broad emission lines, emit over broad wavelength range, and are highly variable. So the emission line regions that I've mentioned previously are made up of gas clouds that are photoionized by the accretion disk emission, yielding the characteristic emission lines from observed AGN spectra that we see here in the upper right-hand plot, which shows an example AGN spectrum in blue versus a normal quiescent spectrum in red. These broad and narrow emission lines cover a wide range of ionization states, which gives us information about the ionizing continuum, but also the width of the broad line tells us how fast the gas clouds are moving, and then can be used along with an estimate of the size of the broadline region to determine the mass of the black hole. So as shown on the plot on the left, AGN emit over the entire wavelength regime with the largest differences at radio frequencies. The UV to infrared continuum is characteristically dominated by two features: the big blue bump, which is produced by the accretion disk, and the infrared excess, which is due to the reprocessed dust emission from the torus. And the figure on the right shows an infrared broadband SED of NGC 3783, which was model fitted using the CAT3D dust radiative transfer model of the torus. So this dusty torus is one of the major obstacles to studying this supermassive black hole growth phase, because as mentioned in the previous talk, it obscures our observations of the light from the accretion disk and the broadline region. And this dusty region also contributes a significant fraction of the AGN's infrared luminosity and acts as a fuel supply for the supermassive black hole. So for these reasons, it's important to understand the properties of these obscuring infrared dusty structures. So because the angular size of these dusty structures is so small, it can't be observed through direct imaging, but it can be studied through interferometry and time variability. So for instance, thanks to the gravity collaboration within the last few years, we've been able to probe the hot dust regions for a handful of AGN that are nearby. And here we have the near-infrared interferometric reconstructed image of the inner few parsecs of the very well-studied AGN NGC 1068 on the left, and on the right, we see a schematic of the inner 5 parsecs of the torus that has been constructed by combining water maser, mid-infrared, ALMA, and these near-infrared interferometric observations. Our unification models, like I showed before, assume that the obscuring dust structure is in the shape of a circumnuclear torus. However, within the last decade, it's been shown that a substantial amount of the mid-infrared emission from AGN is actually found to be elongated along the polar axis. This is proposed to be the result of dusty outflows due to accretion disk radiation or thermal pressure, although the mechanism is still not clearly known or understood. So our observations of the infrared dust emission from AGN have shown us that obscuring dust structure is not as simple as this donut shape that's been previously proposed, but rather a combination of inflowing circumnuclear disk component that mixes or transitions into the dusty broadline region clouds and then gets heated and pushed out by the accretion disk radiation pressure into outflows, causing a dusty bipolar wind. So for simplicity though, I'm still going to refer to this region as the torus throughout the rest of this talk. I've also mentioned before that AGN are highly variable across multiple wavelength regimes. So for instance, that a variability can range in timescales from hours to years, where the shorter wavelength emission has the shorter timescale variability. So for instance, here we see the 5 light curves for MCG 63015 that was monitored for about 5 years in the X-ray from the top panel, the optical in the next 2 panels, through the infrared in the last 3 panels. So each of these wavelengths probe a different region of the AGN, where the X-rays emitted by the hot coronal region that is above the accretion disk is very close to the central supermassive black hole. The optical is from the accretion disk, and the infrared is from the dusty torus. It's also been proposed that periodically varying emission from AGN is a signature for a supermassive black hole binary. The most famous and well-established candidate for a sub-parsec supermassive black hole binary is OJ287, which can be found in the Camosa et al. Paper 2021. But recently, the first possible detection of a binary in spiral of 2 supermassive black holes driven by gravitational wave radiation has been reported by this paper from Zhang et al., which reports the first system of a rapidly decaying periods observed in the optical and X-ray light curves, which has decreased from about 1 year to a period of about a month in just the last 3 years. So here I'm showing the optical UV and X-ray light curves for this object, where the region encased by the dashed box is the SWIFT data, which is shown zoomed in inset at the top for clarity. The modeling from this paper of the orbit suggests that the black hole could merge as soon as 100 days from now. So keep an eye out for that, just in case. So as mentioned in the previous 2 talks, there have been known that changing or transient events can occur in AGN, such as changing look AGN or tidal disruption events, for instance. So although AGN can typically show consistent variations over time, they can undergo these transient events like this flare that we see here for the light curves of NGC 6418, where the optical data is shown in gray and the infrared Spitzer 3.6 and 4.5 micron data is seen in blue and red respectively. This AGN was part of a monitoring campaign aimed at reverberation mapping 12 AGN in the optical and mid-infrared, and then where we observed this sudden rise by at least a factor of 2 in both the optical and infrared. And if you want more information about this particular object, you can see Ashley Frank's poster later on. But thanks to spectroscopic follow-up, we were able to determine that this AGN was originally classified as a type 1.8 AGN, and then it changed its look during this flare to a type 1 AGN. So here I'm showing the various optical spectra that we have found or obtained for NGC 6418 from 2000 on the bottom to 2018 at the top. The spectra have been spatially offset for clarity. In the spectrum at the bottom, you can see that the H beta line is essentially non-existent and the broad H alpha line is present but very weak. However, the following spectrum in red is the one that's taken right after the flare was observed, showing the strongest H beta and H alpha emission lines. And then afterwards, the broad emission lines vary over a few years, but remain much stronger than the original spectrum that was first taken in 2000. So many of these changing look AGN have been found through archival data searches, both in the optical and infrared, with only a handful being caught in the act, such as this object has been observed. We've also been able to see changing look states in the X-rays as well. So this is nice for some follow-up. So another interesting note about this particular AGN is not only did we catch the AGN changing its look and flaring in the optical and infrared, but our reverberation mapping results have shown that the infrared emission was found to increase its lag relative to the optical emission, implying an increase of the size of the dust emission region, or in other words, the innermost dust has appeared to sublimate. So this is an important result as it shows how closely tied the emitting dust region is to the AGN luminosity and how transient events and can affect the evolution and structure of the dusty region. However, as I mentioned before, the size of the torus is too small to directly image. So another way of studying this time variability, to study the time variability, is to study the time variability of the infrared dust emission through reverberation mapping. So As Jort mentioned earlier, reverberation mapping or dust echo mapping uses the fact that due to the time it takes the light to travel from the accretion disk to the dust in the torus, the infrared response will thus lag behind the optical emission. That lag provides a measure of the size of the dust emitting region, but in addition, it contains information about the geometry, structure, and properties of the torus, because the infrared response, which is shown in red on the bottom right-hand plot, is the convolution of the AGN UV optical light curve, which is shown in gray in the same plot, with a transfer or a response function, which is shown in upper left-hand plot. The transfer function describes the emission response to a dust distribution, a delta function continuum pulse. So in my research, I studied the properties of accreting supermassive black holes when they're observed as AGN by analyzing their variability using the reverberation mapping technique. One way we've been doing this is by developing a computer simulation called TORMAC, which calculates the time-dependent response of the torus infrared emission to variations in the AGN UV optical continuum emitted by the central source. In simple models, the lag between the optical and infrared light curve gives a radius of the dust emitting region. In reality, the situation is much more complicated, and the infrared response contains much more information about the torus structure than just its size. So we've been using this code TORMAC to identify the key parameters that affect this response within the clumpy torus paradigm to help interpret the observed lags and extract structural information about the torus from data obtained through infrared reverberation mapping campaigns. So TORMAC can model the dust emission light curves for a 3D ensemble of clouds at multiple infrared wavelengths for direct comparison to the observed light curves using an observed optical light curve as the input signal. This means that you can do this for any type of object, not just AGN, but I'll be talking mostly about AGN in this talk. So each of the clouds' dust emission is derived from a pre-computed grid of dust radiative transfer models, which can be replaced by grids computed for other illuminating continuum sources or other grain mixtures. And TORMAC includes radiative transfer effects both at the cloud level and global level, as well as anisotropic illumination by the continuum source. So recall the light curves of NGC 6418 that I showed earlier. One of the main motivations for creating this code was to compute the dust emission response light curves for any input light curve, including ones derived from observations. So we used TORMAC in order to compute simulated light curves for selected models using the optical light curve of NGC 6418 as the input. And here's an example of the model light curves at 3.6 microns, represented by the solid colored lines, computed using the mean interpolated observed optical light curve of NGC 6418 as the input, which is plotted in gray. The observed Spitzer 3.6 micron light curve is shown as the blue pluses. We are currently compiling a grid of model light curves covering a large parameter space and then using an adaptation of the MCMC code Clumpy Dream, which was created by Jack Gallimore, in order to search within this model grid to fit the observed infrared light curves and generate probability distributions of the best fit torus parameters. However, we've also used this code in order to conduct the most comprehensive investigation to date on the dependence of this dust emission response to the structure and orientation of the torus, including opacity and illumination effects. First, we wanted to see how well the measured lag derived from reverberation mapping, or the response weighted delay, measures the effective radius of the dust distribution, or the luminosity weighted radius. In the idealized case where we have a globally optically thin torus filled with isotropically emitting clouds, it can be shown that the response weighted delay exactly equals the luminosity weighted radius. However, this isn't obvious that it still holds when the effects of radiative transfer, such as cloud shadowing and occultation and anisotropic illumination, are included. Thus, here I'm showing the relationship between the response weighted delay, or the reverberation mapping lag, on the y-axis versus the luminosity weighted radius, or effective radius of the dust distribution, on the x-axis. Each of the gray points represents a model response function that was simulated within a large range of parameters at 3 different infrared wavelengths. The diagonal black line represents the idealized case where the response weighted delay exactly equals the luminosity weighted radius, and the colored lines represent the best fit lines to the models for each wavelength where the corresponding slopes are shown in the legend. The scatter that we see here is wavelength dependent and mostly due to input structural parameters such as the radial cloud distribution, the volume filling factor, and the inclination. Despite the scatter though, the response weighted delay was found for these models is found to be within a factor of about 2.5 of the luminosity weighted radius at most. This tells us that the lag that's determined from the torus response is a reasonably robust measure of the effective radius of the dust distribution within a factor of 2, regardless of the detailed properties of the torus, which are not well constrained by observation, such as geometry, inclination, cloud distribution, and radiative transfer effects. So this result is important because when the distance corresponding to the measured lag is plotted against the AGN luminosity, it's found to follow a power law slope of 0.5, which is the same dependency found for the theoretical dust sublimation radius. On the plot, we see the results from previous reverberation mapping work that's been done in the K-band as the black points, with their average, the average slope shown as a solid orange line. And the radii determined from reverberation mapping methods tends to be smaller than that from the theoretical dust sublimation radius for ISM grains, which is shown as a black solid line, which have a sublimation temperature of about 1500 Kelvin. So several explanations have been proposed to explain this discrepancy, such as including an inner component of hot graphite dust or large grain sizes, which have a higher sublimation temperature, or anisotropic illumination of the torus. So during our parameter space investigation, we wanted to try to see if we can answer such questions as the discrepancy between the theoretical and observed reverberation mapping radii. So here I'm showing the same K-band observed reverberation mapping radii as before, as the black points, along with the theoretical lines for the dust sublimation radius for ISM dust composition in black, and carbon grains, which has a higher sublimation temperature of 1800 Kelvin in gray. Also shown is the shaded blue and red regions, which represent the range of radii predicted for a subset of my models for isotropically and anisotropically illuminated tori respectively. So as you can see here, the models barely match the observations. Thus, dust distributions of clouds with only an ISM grain mix composition and anisotropic illumination alone cannot explain the discrepancy between the theory and observations. The data points actually seem to scatter around the graphite sublimation radius, suggesting that the innermost clouds have a graphite dust composition. To account for this, my undergraduate student from the University of Southampton, Nadia Konikova, adapted my code in order to include this inner hot graphite dust component by using a different radiative transfer grid for the dust cloud emission obtained from Sebastian Honig's CAT3D simulations. So here I'm showing the same radius luminosity relationship I showed in the previous slide for only the isotropically illuminated models with the ISM only dust clouds in blue and including a hot dust component in the light blue. As you can see now, the models completely encompass the observed data without even having to invoke or include anisotropic emission or illumination. However, as we know, the dust is illuminated by an accretion disk. So here the model results for an anisotropically illuminated dust distribution, where the red represents the ISM only dust and the magenta includes the inner hot carbon component. The scatter in the observed radius luminosity relationship is relatively small compared to the band that's covered by my models, which suggests that actually the parameter space can be further restricted, and we're currently working to identify the parameters that most likely explain the observed scatter. So one of the most important conclusions from this work with TORMAC so far is that the response weighted delay is typically within 0.4 to 2 times the luminosity weighted radius for each model. This result is important for the interpretation of results from infrared reverberation mapping campaigns, because when we measure the optical infrared lags from observed light curves, reverberation mappers can be confident that their estimated torus size is about representative of the effective radius of the torus at the wavelength to within a factor of about 2. This is important for the current work we're currently doing with the VALES campaign, which will increase the number of dust reverberation mapped AGN and will provide a major step in understanding the torus with respect to AGN luminosity and redshift, but will also hopefully establish AGN as an independent cosmological standard candle. So VALES, or the VISTA Extragalactic Infrared Legacy Survey, uses the infrared camera on the VISTA telescope in Chile to monitor 3 regions within the DES field of view in the J and K band over 4 years, resulting in the largest infrared reverberation mapping campaign conducted so far, covering a total of 9 square degrees and monitoring several hundred AGN. So in my last postdoctoral position, I led the infrared data reduction and analysis for this campaign, and 3 years of the data have been fully reduced, and I've extracted the infrared light curves for nearby variable AGN. So along with our complementary optical data, we're starting our preliminary time series analysis. One of the aims of this survey, as I mentioned before, is to increase the number of dust reverberation mapped AGN by an order of magnitude, so that by the end of this survey, we'll have a vastly expanded database of hundreds of AGN light curves for which we can then use to study the properties of the torus with my code to a redshift of about 1.2. One of the other big things is that given the tight relationship between the measured lag and the AGN luminosity, we'll be able to use the lags as a proxy for the AGN luminosity, where we can then determine the distance modulus and plot that versus redshift in order to construct a Hubble diagram to help constrain cosmological parameters. And when combining—
5 minutes.
No problem. So when combining the AGN and supernova data as shown on the plot on the right, we have this gray region, which helps constrain those cosmological parameters even further than having the independent cosmological standard candles. So what AGN science can we do with Roman? So there's many open questions in AGN studies. However, I'm going to just, because of the scope of this conference, I'll just highlight some of the time domain and infrared AGN science that can be done with this telescope. Oops. So for instance, on the time domain side, we're still trying to understand the accretion disk physics and variability, the nature of the hot dust component and the interface between the torus and the broadline region, what causes these extreme transient luminosity variations that we've just heard about from the previous two talks as well as in AGN, and then the detection and demographics of supermassive binary black holes and mergers. So long-term monitoring of AGN, particularly of well-sampled multiband optical infrared light curves over long time baselines, will be important and vital in resolving these open questions. So for instance, the Roman telescope is the only upcoming time domain survey that can reach up to 2.2 microns, which probes the sublimation region of the AGN dusty torus. Thus, we will be able to exploit the time domain surveys of Roman and expand our sample or continue monitoring some of the hot dust reverberation mapped AGN that have previously been found. Also, given the wavelength range covered by Roman, we can reverberation map and study the accretion disk physics over a larger redshift range, since Roman will be able to probe the accretion disk variability into the near infrared at higher redshifts. On the non-time domain side, Roman can be used to detect and observe AGN out to redshifts greater than 7, allowing us to study AGN at the faint end of the AGN luminosity function, allowing us to study AGN at high redshifts, as well as the coevolution of supermassive black holes and their host galaxies during the epoch of reionization, including feedback mechanisms and the effects of and their influence on the cosmic environments, as well as the origin and evolution of the first supermassive black holes. So here I'm showing the results from a recently published from the Subaru high redshift exploration of low luminosity quasars by Matsuka et al., showing hundreds of objects above a redshift of 5.6 that have been detected in the optical and infrared on the left. And on the right shows the distribution of the spectroscopically confirmed high redshift objects by color, showing the distinction between the AGN and galaxies versus the stars, and blue and green to red respectively, as predicted by models. So Roman has the capacity to greatly increase the sample size at redshifts greater than 6 by an order of magnitude. So last but not least, Benjamin Rose gave a great talk yesterday of all of the synergy that can be done with other telescopes along with Roman, and give us a better understanding of extragalactic and particularly AGN science. So for instance, by combining data from upcoming time domain surveys such as Rubin, SDSS5, Roman, and Euclid, we'll have a very long time baselines and samplings of AGN light curves across a broad wavelength range, which will allow not only reverberation mapping of the dusty torus, but also of the broadline region and accretion disk, giving us insights into the physics and variability of individual AGN components and the relationship with each other for a variety of AGN. Also, by combining contemporaneous multi-wavelength follow-up observations from the radio to the X-rays, we'll be able to study and model the evolution of AGN SEDs over cosmic time. Also, multi-wavelength follow-up observations using observatories such as James Webb and ALMA will yield high-resolution kinematic and spatial features for these AGN. And lastly, rapid synergistic follow-up of discovered transients such as tidal disruption events or changing look AGN can help us understand how these large variations affect their immediate and large-scale surroundings by allowing us to map and monitor these changes over time. sorry, I didn't put up that bullet. So in a nutshell, the Roman telescope, along with other upcoming time domain surveys, will allow us to explore the demographics and populations of AGN, black holes, and quasars over a large range of luminosities and redshifts, giving us a better understanding of AGN over cosmic time. Thank you, and I'll take any questions.
Great, thank you for a wonderful review and a great talk. Short has a question in the Zoom chat, which says, the hot graphite dust is also needed to explain most of the TDE dust echoes. Do you also have constraints on the AGN dust temperature from the IR colors or mid-infrared spectra?
So with respect to the dust temperatures, some of the SED modeling, like I showed previously from, let me see if I can pull up the slide. Well, here's a good example. For instance, this is a TORUS SED model that includes that hot graphite dust component. And so the 2 microns doesn't probe the peak, for instance, of the infrared dust emission. However, it is probing that sublimation region that is varying more rapidly over time than some of the more infrared time. So the temperature of this graphite dust that sublimate is about 1700 Kelvin or 1800 Kelvin, and that's about what we're probing, we think, at this 2.2 microns. Hopefully that answered your question.
All right, we have another question in Slack from Cyril, which says, great talk. Do you have any intuition on whether Hubble inferred from time lag measurements is better or worse than Hubble inferred from variability timescale measurements?
I'm sorry, can you repeat the question? If Hubble...
Yeah. Whether Hubble inferred from time lag measurements is better or worse than Hubble inferred from variability timescale measurements. So I think the question is asking whether you do better with lags or whether variability, like the time scale of the variability does a better job for cosmology.
I think so. Okay, for cosmology, I would say that the time lags, well, okay, so with Hubble, you wouldn't be able to probe the dust of the time lag. So I didn't show this, but the broadline region lags and accretion disk lags that are determined from, that would be in the optical bands are not as tightly constrained as I showed for the RL relationship for dust. So the dust lags are definitely much more constrained and have a tighter relationship with the AGN luminosity than the broad and optical emission does. Hopefully that answers the question. So basically, I think the time lags do have quite a robust tight relationship with their AGN luminosity. However, in the optical regime, it changes with respect to which band you're probing. And so we need to have better diagnostics, for instance, of the broad lines emission and variability, as well as accretion disk emission and variability, which is still not very well understood, versus dust reprocessing, which is much more simple to understand and not as widely variable as individual optical bands are.
Great. We have another question from Gisela De Rosa, which is, do you think that current plans for Roman time domain surveys would be okay for dust reverberation mapping? Or would you need targeted RM programs to do?
So from what I understand of the high latitude time domain surveys and things like that, the short answer is no, it's not going to be enough. What we truly need is long-term monitoring. So for instance, having these 5-day cadences, although it's very nice, especially if you have low luminosity AGN, which vary over shorter timescales. However, AGN tend to vary more on week to month timescales. So we need more repeat observations of a particular field versus really high cadence over a shorter period of time. So we need more long baseline to see the longer timescale variabilities versus the shorter timescale variabilities.
Okay, we have another question from George Hellu, which says, it's about your models. Do your models of infrared emission include very small grain populations that respond stochastically to single photon heating?
Yes, but also we don't do it to that level. So although the radiative transfer models I'm including do have a grain mix, so it's an MRN grain mix, we more model the emission of a optically thick dust cloud or a clump. And so those are what we're modeling with respect to those like, oh shoot, what's the word? To the, like immediate time emission, however, not necessarily of individual grains themselves, if that makes any sense.
Okay, we are out of time, but Triana, there is another question on Slack if you want to go answer that. And other folks, if you think of questions, feel free to ask them on Slack as well.